to uses for nuclear technology and nuclear reactions. You might be asking, nuclear, huh? What is it good for? It's actually good for lots of stuff. Here are some common examples of some uses for nuclear technology. These are, by far not the only things that nuclear technology is used for, especially in medicine. There are many more examples of radioisotopes that can be used medically, but these are a few common examples that you're expected to know. Iodine-131 is used for detecting and curing hypothyroidism. Iodine is actually in salt. You might notice salt says iodinized on it because your thyroid requires iodine. So iodine-131 will actually be taken up by your thyroid and can be used as a tracer. Iodine can also be used as a treatment for someone who has radioactive iodine, that is, for someone who has thyroid cancer. Cobalt-60 is also a radioisotope used in the treatment of cancer. And technetium-99m is actually used as a tracer that can help to image blood vessels in the brain and help detect tumors. What's important about all of these is that they all have relatively short half-lives, which allows them to be eliminated from the body fairly quickly. Our isotopes for energy and our military isotopes are actually one and the same since, we'll just use one big box there, sorry. Since nuclear fission is at the heart of how both of these technologies work. Nuclear fission generates a large amount of energy. Uranium-235 is what's used in most fission reactors. In terms of plutonium-239, this is not really commonly used and is more likely to be used in nuclear weaponry. In both cases, you're doing reactions that have a lot of energy involved with them. They're releasing a lot of energy. In a nuclear power plant, you're simply controlling the amount of energy being released. Whereas a nuclear bomb, you're letting the reaction go. In your home, americium-241 is used in smoke detectors. It actually is an alpha emitter. Those alpha particles hit a detector. If smoke blocks the alpha particles from hitting the detector, your smoke alarm will go off. It's actually a man-made element. Since it's past 92, it's past uranium on the periodic table. In science, there are two ways that we can determine how old something is. It depends on whether or not it's alive, which one we choose to use. If we want to determine the age of something biological, so some biological remains, like an archaeologist might dig up some bones, you use carbon-14 radiodating, which you learned about in earth science. Uranium-238 is used in geologic dating of rocks. So rocks actually, if you find a fossil in them, you might be able to find some carbon, but for the most part, rocks don't possess a lot of uranium in them. So geologists depend on uranium decay series in order to determine how old rocks are. Uranium also has a much longer half-life. Geological things tend to be even older than biological things. So nuclear reactions actually release a ton more energy than chemical reactions, which probably makes sense if you think about like nuclear power plants and nuclear bombs. The reason for this is a very famous equation that you've heard of called E equals mc squared. And what this stands for is energy equals mass times the speed of light squared. You don't need to know what the exact value for the speed of light is, but I'll tell you that it's 3 times 10 to the 8th meters per second. What you probably do know about this is that it is a large number. It's fast. So what's actually happening here, if you think about this equation, we're taking a small amount of mass and multiplying it by a very large number, which is the speed of light squared. In any nuclear equation, a very, very small amount of matter or mass, very, very small amount, gets turned into a very large amount of energy. If you wanted to calculate that amount of energy, we use that famous Einstein equation, and that's why we get such a big, huge number. There are many things that affect the rates of chemical reactions, such as heat, pressure, catalysts, surface area, concentration. Rates of nuclear reactions are not affected by any of these. Nuclear reaction rates are fixed. So the rate of the half-life, for example, for carbon is fixed. It doesn't matter if a dinosaur bone is found somewhere really warm or really cold, that nuclear decay of the carbon in that bone is a fixed rate.
Kind of attention, please, Brian Ambos, your knee.
So two major categories of nuclear reactions, kind of two subcategories we look at too. Anytime we talk about natural decay, which was what we began our unit talking about, we talk about an isotope that is found in nature that is naturally radioactive and spontaneously decays. That nuclei is unstable, so it spontaneously decays. And it might decay to something else that's also unstable, or it might decay to something stable. What helps you identify this is that on the left side of the equation, there's only one thing there. This is happening on its own, so it does not need to be bombarded by another particle. There's destruction of mass here that is releasing energy. So nuclear decay equations do have an amount of energy being released with them. Artificial transmutation, you'll notice we have one particle being bombarded with another one. So we actually, the plus sign here is indicating that an alpha particle is bombarding that plutonium. The initial nuclei could be unstable. It's not necessarily going to decay on its own. We bombard it with another particle, making it less stable, and then it will continue to decay. The left side of one of these equations will have two reactants because one is bombarding the other. Although this does still release a lot of energy, there's also a large input of energy, so it's a little bit of a wash. Things that are common to both, these are both transmutations. Remember that word from the beginning of the unit. They both form new elements. When we balance them out, they both have equations that balance for mass and charge. That amount of energy that's lost is so small, it doesn't actually show up when we look at our mass numbers. And we have a very small amount of mass being converted into energy by that E equals mc squared equation in both of these types of nuclear reactions. Fission and fusion are kind of a couple of beasts on their own. Nuclear fission is very much an artificial transmutation. Nuclear fusion kind of looks like one in a way, but it's actually naturally occurring. Nuclear fusion is when small nuclei combine to make a larger nuclei. Specifically, in this case, we have 4 hydrogens, which are very small, combining to make a helium, which is bigger, okay, it has a mass of 4 as opposed to a mass of 1. This is also, in this case, accompanied with a release of positrons and a whole lot of energy. This reaction occurs on the sun. So it does occur naturally. So you really say that this is a natural transmutation, although it's not really a decay. It is kind of like that particle bombardment idea. This is really able to happen there because it's very, very hot on the sun. So you actually need very specific conditions of heat and pressure for this to happen. And the extremely high temperature of the sun is very important for this. Nuclear fission is a splitting of larger nuclei into smaller nuclei. When you talk about binary fission as a form of cell division, it's the same concept, something splitting. We do have to bombard for this to happen. So we actually take a neutron, we bombard the isotope uranium-235. Turns briefly into uranium-236, which is unstable, and then it decays into krypton and barium and also releases 3 more neutrons. This is accompanied with a large production of energy. That energy can be used to boil water, which turns a turbine in a nuclear power plant. This can also be a less controlled reaction that creates a lot of heat and is utilized in a nuclear bomb. What's interesting about this reaction is the product is these 3 neutrons right here. Those 3 neutrons can actually go and each start another fission reaction. So this is actually a chain reaction. If each one of these guys starts another reaction, Each one of those reactions will let out 3 more neutrons. Each one of those will let out 3 more neutrons, etc., etc. So you can see the, you know, possibility of a very uncontrolled reaction here. In a fission bomb, you just simply allow those reactions to continue to occur. In a nuclear power plant, control rods are used to prevent some of those neutrons from starting new reactions. You do need to be able to recognize these two equations. You don't need to be able to specifically write them out, but you do want to recognize that nuclear fission includes uranium, whereas nuclear fusion is when we are adding together hydrogens to make a helium. In nuclear fission, that's a splitting, whereas fusion is a fusing. Fission is unknown in the natural world, whereas fusion is what powers the stars and the sun. Fission can take place at any heat and temperature. We can do it here on Earth. Fusion requires very high temperature, especially in pressure as well. We currently use fission to make electricity. People are trying to use fusion to make electricity, but have not succeeded yet. Fission requires that we mine for uranium, which is found naturally in rocks, really all over America, all over a lot of other places. Hydrogen is extremely abundant in the environment. Unfortunately, we really don't have a way to utilize that hydrogen in our, a reaction vessel to do fusion for energy. There's a lot more energy created by fusion than there is fission. This is a much more energy-intensive process, or energy-producing process. Big plus of fusion is that it does not produce much radioactive waste, whereas there's a lot of radioactive waste produced with nuclear fission. So you may be wondering why, if this nuclear waste is, produced, and if it has to be stored on site, and it's pretty dangerous, and we can't really use it or move it, what are we going to do with it? Why do we do that? Currently in New York State, we're running, well, right now I think we're still running 6 nuclear power plants. That is about to change. Nuclear power can generate a lot of electricity without contributing to smog very much. So what's really nice, this is kind of an older stat, but you can look at the numbers here. Nuclear power plants in New York State avoid a lot of emissions like SO2, which causes acid rain, nitrogen oxide emissions, which make smog, and CO2, which contributes to global warming. So the upside of this is nuclear power is a clean air fuel. The downside of this is there's a lot of metric tons of used fuel being stored currently on site at many of these nuclear power plants.